Welcome to the Explainer. Today, we're taking the messy, chaotic, multi-directional motion of the real world and translating it into the incredibly elegant language of vector mathematics. I mean, have you ever tried to describe exactly how a bird flies through the air or how a boat gets pushed off course by a river current? It turns out basic everyday math just isn't quite enough to tell the whole story. But today, we're going to unlock the specific mathematical tools that make sense of it all.
Here's our roadmap for today. We're going to start by moving beyond the straight line, then we'll learn the language of vectors, break them down, check out the math of vector addition, and finally, define motion in full 2D.
All right, section 1, beyond the straight line. Let's dive right in by looking at what we already know, and more importantly, where that knowledge completely hits a wall.
Think about tracking a train on a straight track. Your life is pretty easy, right? It's either moving forward or it's moving backward. Positive and negative signs work great for this kind of one-dimensional motion. But those simple plus and minus signs absolutely fail to describe an object moving in a flat plane or in three-dimensional space. How on earth do you use a plus sign to describe a bird soaring upwards and to the right, or a car hitting a curved off-ramp? Well, you can't. We need a totally new way to describe these physical quantities.
So we've got to upgrade our mathematical toolkit. On the left, we've got scalars. A scalar quantity is something with magnitude only. It's completely specified by just a single number and a unit. Think of the distance between two cities, the mass of a bowling ball, or the temperature outside. You just use ordinary, everyday algebra to add or subtract them. But on the right, we have the real game changer, vectors. A vector is a quantity that has both a magnitude and a direction. Velocity, displacement, acceleration, these are all vectors. To accurately map the real world, we need to know not just how much or how fast, but in exactly what direction.
Moving on to section 2, the language of vectors. Let's actually see how this builds visually before we even think about touching an equation. So, vectors are visually represented by arrows, where the length of the arrow is the magnitude and the way the arrow points is obviously the direction. Now, what if we want to combine two movements? Look at the two methods we have here. On the left, the triangle method, which is also known as the head-to-tail method. We just place the tail of vector B right at the head of vector A, and the resulting line from the start to the finish is our sum, our resultant vector R. On the right, we've got the parallelogram method. Here, we bring the tails of both vectors to a common origin and draw parallel lines to create a parallelogram. That diagonal line slicing right down the middle, that's our resultant vector R. And this brilliantly illustrates how arranging vectors head to tail or from a common origin both lead to the exact same resultant vector. It's the same physical truth, just drawn two different ways. Kinda cool, right?
All right, section 3, breaking vectors down. Now that we can draw these things, we need a way to deconstruct those kinda scary diagonal lines into safe, manageable, bite-sized pieces.
To pull this off, we use something called a unit vector. It's exactly what it sounds like, a vector with a magnitude of exactly 1. It has no units, no dimensions. Its only job in life is to point in a specific direction. In our standard rectangular coordinate system, we use unit vectors called I hat, j hat, and k hat to point along the x, y, and z axes. By anchoring these unit vectors along our axes, we're basically building a universal grid for all of our physics problems. What's absolutely fascinating here is how we can take literally any random vector pointing off into space and just snap it right onto that universal grid. Look at vector A here. By dropping perpendicular lines straight down to the x-axis and straight across to the y-axis, we turn one complex angled vector into two simple perpendicular shadows, A sub x and A sub y. We call this process resolving the vector into its components. And because these components form a perfect right triangle with the original vector, we can use some basic trig to lock them in mathematically. As long as we know the total magnitude of the vector and the angle theta it makes with the x-axis, we are good to go. The horizontal component, ax, is simply a times the cosine of theta. The vertical component, ay, is a times the sine of theta. Boom! Just like that, we've translated a visual drawing into hard, workable numbers.
Which brings us to section 4, the math of vector addition. Let's see how breaking these vectors down makes combining them incredibly easy. We're leaving the drawings behind and diving into pure analytical math.
Remember those triangle and parallelogram drawings we did a few minutes ago? Great for visualizing, sure, but honestly, they get super tedious and frankly a bit inaccurate if you're trying to add 3, 4, or 5 vectors together. By resolving vectors into components first, addition becomes an absolute breeze. You don't need a protractor anymore.
Instead of drawing complex shapes, we literally just add the horizontal pieces together to get our new x, and the vertical pieces together to get our new y. It's exactly like balancing a simple ledger. Rx equals Ax plus Bx. Ry equals Ay plus By. It is beautifully, wonderfully straightforward.
And finally, Section 5, Defining Motion in 2D. We've got the mathematical tools. Now it's time to unleash these vectors onto real, dynamic motion in a plane. Picture an object moving along a curvy, winding path. If we look at where the object started and where it ended up after a certain amount of time, we can draw a displacement vector straight between those 2 points. Divide that displacement by the time interval, and you get the average velocity. But average velocity doesn't tell us what's happening at one exact split-second moment. To get that precise speed and direction, we have to take the mathematical limit as our time interval shrinks closer and closer to zero.
This right here is the absolute magic of limits in calculus applied to physics. As that time interval shrinks to zero, the displacement vector gets smaller and smaller until it perfectly touches the curve at exactly 1 point. Visually, this means the instantaneous velocity vector is always perfectly tangent to the curved path the object is taking. Think about it. If you're spinning a rock on a string and the string suddenly snaps, the rock flies off exactly along that tangent line. Every single time.
Okay, let's put everything we've learned to the ultimate test with a real-world scenario from the source material. Imagine a motorboat. The driver has the boat pointed straight north with the engine providing a velocity of 25 kilometers per hour. But the water in this region isn't sitting still. There's a water current pushing at 10 kilometers per hour in the direction of 60 degrees east of south. So, where does the boat actually end up going? This is a classic textbook two-dimensional vector problem. Take a look at the diagram. We draw the boat's velocity vector pointing straight up, north. Then, from that exact same common origin, we draw the water current's vector pointing down and to the right, 60 degrees east of south. Because they share that common origin, we can use our trusty parallelogram method to draw the resultant vector r. And since we know the angle between our two starting vectors is 120 degrees, we can just use the law of cosines to figure out our exact resultant path. When we actually crunch those numbers, squaring the 25, squaring the 10, factoring in that 120-degree angle, the math proves the boat is shoved way off its straight northern path. The actual resultant magnitude, meaning the true speed the boat travels relative to the shore, is about 22 kilometers per hour. And if we use the law of sines, we'd find it's drifting about 23.4 degrees east of north. The math perfectly predicts reality.
We've covered a ton of ground today, moving from the limitations of a simple straight line into the dynamic, vector-driven world of two-dimensional motion. By breaking complex paths into simple x and y components, the chaotic movements of the real world become totally solvable. So I'll leave you with this. The next time you look out the window, don't just watch things move. Imagine the vectors. How would you draw the mathematical arrows for a thrown baseball, a falling autumn leaf, or a car taking a sharp turn? Now that you speak the hidden language of motion, I promise you, you're never going to look at a moving object the exact same way again. Thanks for joining me on this explainer, and keep questioning the physics of the world around you.